Okay, folks. So this time in this series of videos, it will be the chapter of nuclear physics. So in our class, it is chapter 5, uh, which is the nuclear reaction. And there are 3 subtopics. Okay, so this first video will cover subtopic 5.1 and subtopic 5.2. Okay, so first 5.1, it will be about the expression that the scientific expression used to express nuclear reaction or to indicate nuclear reactions. And in 5.2, what is the energy produced in a nuclear reaction? It involves the uh, quantitative calculation about the Q value. And finally, 5.3 is the uh, fundamental of nuclear reactions, which is the cross section, be it nuclear cross section or scattering cross section. So what you see now, 2H and gamma 3H, and then 2H dp 3H as well as 6 LiP alpha 3H. So this is how this notation about a nuclear reaction. And I will go back to this notation later on. Okay. So we will look at the fundamental first. Okay, so nuclear reaction is a nuclear process. So the process occurring inside the nucleus. And as we all know, radioactivity is the process that occurs inside the nucleus. Okay, so radioactivity is also a type of nuclear reaction, but it is spontaneously occur. Okay? And because of the spontaneous occurrence in the radioactivity, okay, so we call it decay process. Okay? It is nuclear reaction, but we usually not referring it as nuclear reaction because of its spontaneously occurring in nature. So it is called a decay process, but not nuclear reaction. Okay. It is a type of nuclear reaction. Okay, but we don't call it nuclear reaction, but we call it decay process. Okay, and as opposed to that, okay, the non-spontaneous nuclear reaction, okay, which is the focus in this chapter, okay, is induced, okay, or is initiated by the bombardment of particle or electromagnetic radiation that is high in energy. Okay. So radioactivity, you do not you don't do anything, okay, to induce radioactivity because it is spontaneously occur. Okay, like in the alpha decay. Okay, so the parent decaying, giving us the daughter as well as alpha particle. Okay. So you don't need any you don't need any trigger. Okay, because the process spontaneously occur. So the decay process spontaneously occur. Okay. But for other nuclear process, uh, for example, okay, for example, the most the most applied nuclear reaction on the earth at the moment, okay, which is the nuclear fission. Okay, you have uranium 235, so you need to bombard the uranium 235 with a neutron. Okay, this is supposed to be plus sign, not arrow. Okay, so plus, meaning that the nucleus of uranium 235 is bombarded with a neutron. Okay, that will give you uh, two, in average, two products. Okay, so this is the non-spontaneous nuclear reaction. Okay, the inducement is, in example, is by high energy neutron. Okay, that's that in next chapter, in next chapter, nuclear fission. Okay, we'll elaborate this process in detail. Okay, like in chemical reaction, nuclear reaction will also release energy. Okay? Like we discussed in the uh, in radioactivity, in the decay process in radioactivity, you can calculate the energy from the decay. So similarly, in the non-spontaneous nuclear reaction, okay, you can you will you can get some energy, okay, like in the chemical reaction. Okay. So it involves energy, but if we want to compare the energy release in nuclear reaction versus the energy release in the chemical reaction, it is about 1000 times, okay, bigger than the energy release in chemical reaction. Okay. So energy involved in nuclear reaction is uh, far bigger than the energy involved in typical chemical reactions. Okay, however, both reaction, the nuclear reaction as well as the chemical reactions, should obey the same physical laws, which are the conservation of momentum, conservation of energy, conservation of number of particles, as well as the conservation of charge. And currently, okay, there are about 20,000 isotopes. Okay? So meaning that there are about 20,000 uh, nuclides, okay, that you can put it in nuclear reactions. Okay? But for practical application, okay, there's only few. Okay, like the in fission. Okay, you the practical one is uranium or thorium. Okay? And in fusion, uh, deuterium, tritium. Okay, and then lithium, if I'm not mistaken. Okay, we will. This is in chapter 6. Okay, we will revisit it. Okay, so although you can initiate almost 2000 type of nuclear reactions, but for practicality, okay, for energy harvesting application, the number of isotope is only a few. Okay, okay, like in this example, okay, the bombardment involve uh, uh, an energetic neutron. Okay, and similarly, okay, if it wasn't uranium 235, okay, it could be any nucleus. Okay, so you can initiate nuclear reactions, okay, by bombarding the nucleus with photons. Okay, so it doesn't necessarily have to be particles. Okay, it can also be photons. Okay, uh, especially gamma. Okay, especially gamma ray or X-ray. Okay, that has a very high energy. Okay, and then only then you can initiate reactions. Okay, and then other than photons, the typical particle that are used to bombard the target. Okay, you call this target. Okay, target. The target nucleus are electrons, protons, neutrons, alpha, okay, deuterons, as well as heavy charged particles. Other than alpha, it means that you can have heavier, okay, heavier nucleus, heavier charged nucleus as as the bombardment. Okay. And the deuteron uh is hydrogen nucleus, but with one proton and one neutron. Okay, and hydrogen is on the nucleus of hydrogen is only consists of only one proton. Okay, but deuteron or deuterium is nucleus is one proton and one neutron, and another species is one proton and two neutron, which we call it you call it tritium. Okay, so all these are the isotope of hydrogen. Okay, uh, so okay, just now I explained uranium 235 bombarded with highly energetic neutron. You get two uh, product, okay, two nucleus, okay, X and Y. Okay, other than this, you can also, it is possible also to have particles. Okay, so the product could be X nucleus, Y nucleus, as well as particles. Okay, so meaning that uh, for the reaction, you bombard particle, okay, to the target nucleus. Okay, you get product nucleus as well as particles. Okay, so you have particles coming in as well as particles coming out. Okay, so similarly, okay, the particle that coming out could also uh, be as photons, electrons, protons, neutron, alpha particle, deuterons, as well as heavy charge particle. Okay, so So if this is the target, okay, this is the particle that you bombard. Okay, the product will also become the product nuclei or product nucleus plus particle. So particle in, you have particle in, particle out. Okay, the target and also the product. Okay, and in especially in the fission of uranium 235, okay, it could be more than one product nuclei, product nucleus. Okay, so so in general, uh, uh, so okay, no, so it's not yet equation 5.1. There's another possibility in nuclear reaction. Okay, that you can have two nuclear particle, okay, such as two nuclei, okay, or a nucleon, okay, and or photon and a nucleus, okay, to interact, produce two or more particle or gamma rays. So this statement seems sounds complex, complicated, but to visualize this, okay, two nuclei, nucleon and a or photon and a nucleus interact to produce two or more particles or gamma ray. Meaning that before the reaction, okay, you can have two particles. Okay. So these two particles could be nuclei. So number one, nuclei. Number two is also nuclei. So number one doesn't necessarily have to be uh, a particle. Okay. So this number one also could be a nucleus. Okay. Okay. Or number one is a nucleon. Okay. Nucleon, it could be proton or neutron. Okay. And number two could be a photon or a nucleus. Okay. Uh so the rule is number one doesn't necessarily have to be particle, and number two doesn't necessarily have to be nucleus. Okay. So number one could be nucleus. Okay. And number two could also be photon. Okay. So anything that can works. If there's two entity that can works to produce nucleation, then you will have nucleation. Okay. So the interaction will produce in general, okay, one or two particles, okay, as well as electromagnetic radiation. Okay. So so it doesn't necessarily you will end with one nucleus plus one particle. Okay, you can have more than one type of uh, nucleus. Okay, plus other uh, uh, other products such as photon okay, or other particles. It could be proton, neutron, alpha, okay, as well as heavy charged particles. Okay, there's no general rule, okay, that limits what you can have before the nucleation and after the nucleation. So in general, which is why in general, okay, you write, if there are two type of product after the reaction, okay, then you write the before the reaction, okay, the particle that in the number one entity, okay, the first entity that involved and the second entity that involved, okay. So the product, the first entity of the product, okay, is this one C as well, and then the second entity of the product SD. Okay, so the statement number 9 saying is, if you have two nuclei before, okay, so you can write it as, for example, A and B, okay, and C, if C is a nucleus, okay, so you write as C, and D could be, okay, gamma ray. Okay, so two nuclei A and B interact, give nucleus C plus gamma ray D. Okay, so that's what the mean. That is what is the meaning of equation 5.1. Okay, so this one, okay, conservation of nucleon, okay, charge, momentum, and energy. Involved in nuclear reaction, and we will look into, okay, in this for this lecture we will look in detail about the conservation of nucleon and energy, okay, but the rest we don't do that much in detail. Okay, so this one, okay, another representation of nuclear reaction, okay, other than in equation 5.1, okay, you can also have this kind of notation. Okay, so if you have A in bracket B comma C and then D, okay, it's meaning that A is your target nucleus, okay, B is the entity that you use to bombard the target nucleus A, okay, and C is the product nucleus. Yes, C is the product nucleus and D is the product not product nucleus. D is the particle. So D is the product particle. So for example, oxygen. Okay, so oxygen is target. Okay, the bombardment involve neutron. So in this according to the 5.1, okay, so you have oxygen 16 bombarded with neutron, giving us nitrogen 16 plus this is proton. Okay, this is the nucleus hydrogen, so it's proton. Obviously it's proton. So in this case, outside the bracket is oxygen. This is the target. Okay, this is the bombardment. Okay, this is the product particle, and this is the product nucleus. Okay, so in other words, N is the incident incident particle. Okay, P incident particle is the neutron, and the emission particle is the proton. Okay. So this is still okay. This slide number 7 is still about the notation for nuclear reaction. Okay, we are not yet come into this fundamental law. Okay, that will be later. So okay, so the first one, okay, we will look at the conservation of energy. Okay, so which is the subtopic 5.2. Okay. Which so if I state the conclusion first, okay, the conservation of energy in nuclear reaction will give rise to what we are familiar with, which is the Q value. Like in the decay process, Q value is the energy that you can get in any decay process. So in nuclear reaction, we use the same term Q value, okay, which is the energy that we can get in any nuclear reaction. So to derive the Q value, okay, like in the radioactivity, okay, we have to consider the conservation of energy before the reaction and after the reaction. Okay, so you can predict, okay, whether the reaction can produce energy or not, okay, according to this principle of conservation of energy. Okay, so in equation 5.1, okay, the total energy 5.1 A plus B, you get C plus D. Okay, the total energy before the reaction. Okay, so what are possessed by A and B, okay, involve the sum of kinetic energy, okay, of particle A and B, and their individual rest mass energy. Okay, so before the reaction, the total energy, okay, the total energy is the sum of kinetic energy of A and B, and plus the rest mass energy of A and B. Okay. Similarly, so after the reaction, after the nuclear reaction, let's say the nuclear reaction successfully occur, then the energy after the reaction should involve the kinetic energy of C and D, and as well as the mass energy of C and D. Okay. So if you write it in mathematical expression, okay, so this is before the reaction. So this kinetic energy of particle A and particle B. If you notice, this time I use E, okay, instead of T. Okay, T like in radioactivity, I use T, but in this chapter I use E. But both refer to the same thing, refer to energy. So if you don't like to use E, you can use instead of E, you can use T to indicate the kinetic energy of the particle A. Okay, so this is the kinetic energy of particle A, this is the kinetic energy of particle B, this is the rest mass energy of particle A, this is the rest mass energy of particle B. Okay, before the reaction. Okay, so and this energy, this sum of energy should be conserved. So equal to the total energy after the reaction. So this is kinetic energy particle C, kinetic energy particle D, rest mass energy of particle or nucleus. It doesn't necessarily have to be particle. C could be nucleus C, and the mass energy of particle D. Okay, so if you group the kinetic energy to the left hand side, the mass energy of the rest mass energy to the right hand side, that's what you get as shown in equation 5.3. Okay, so what can be concluded here is that kinetic energy, the difference, okay, or the change in the kinetic energy before this is after, this is before the reaction. Okay, so the difference, okay, is exactly same as the difference in rest mass energy, okay, before the reaction and after the reaction. Okay, for you. Okay, so the right hand side of equation 5.3 is known as the Q value. Okay, like the same, like this is the approach is like what we use, what we did in radioactivity. Okay? Okay, and as okay, so the unit for mass, okay, for the rest mass is in U. Okay, since it is in U, and we know that 1 U is exactly 9.31494 mega electron volt per square C, the square velocity of light. Okay, you can further simplify equation of 5.4 to equation 5.5. So if you know the mass, okay, the mass of the mass of the entity before the reaction in unit U, okay, and after the reaction you can determine the Q value involved in the reaction in no time. Okay, so this possibility that okay, typically, okay, like in fission, okay, like in fission, the mass, okay, before the reaction, okay, so the MA plus MB is bigger than MC plus MD. Okay, so the mass before the reaction is bigger than the mass after the reaction. Okay, so in this case, your Q value will be positive. Okay, so meaning that the kinetic energy after the reaction is greater than the kinetic energy before the reaction. Okay, so meaning that the mass, the reduction of mass, okay, the reduction or the decrease in mass is converted to kinetic energy. Okay, so this, if the Q value is positive, then the reaction is classified as exothermic reactions. Okay, if instead the Q value is negative, okay, so that means that the mass, okay, the mass after the reaction is bigger than the mass before the reaction. Okay, so what this implies is that the kinetic energy before the reaction is now being converted to the mass of the mass of the nucleus or particle after the reaction. Okay, and if Q is negative, the reaction is classified as endothermic reaction. Okay, so in endothermic reaction, okay, instead of getting kinetic energy, okay, the kinetic energy of the particle before the reaction is now converted into mass. Okay, so depending on the application, okay, you use you for obvious, so depending on the application, you have to select the uh, the candidate, okay, the candidate for the reaction, okay, so that you can you can get whether you want, you can get whether the reaction is exothermic or endothermic to fit your application. Okay, and obviously for fission reaction, you want the exothermic reactions. Okay, this example uh, is the conservation of nucleon. Okay. So this particular example will demonstrate the conservation of nucleon. Okay, so if this one, okay, if neutron, not neutron, nitrogen 14, bombarded with neutron, okay, you get proton. And then what is the nucleus? What is the product nucleus? Okay, so now you need to balance the number of nucleons before and after the reaction. Okay, so let me clear screen first. So the atomic number of nitrogen is 7. Okay, this one is 7. And neutron, okay, neutron is not a nucleus. Okay, neutron is not a nucleus, so it's 0. Okay, so the sum of the atomic number on the left hand side of the reaction is therefore 7. Okay, 7 plus 0, so 7. Okay, so according to the law of conservation of nucleons, okay, so since the left hand side is 7, okay, the right hand side must also be 7. Okay, and okay, and since hydrogen, the mass, since we have hydrogen on the left, okay, so obviously hydrogen is 1. The atomic number of hydrogen is 1. Okay, so the total should be 7. Okay, but since uh, we already given hydrogen here, which is 1, okay, so that the rest should be 6. Okay, so 6 should be carbon. Okay, so since z equal 1 for hydrogen, okay, it follows that z of the unknown nuclide is 7. So 7 carbon. So you should have carbon there. Okay, so that's that is the carbon nucleus. Okay, so we know that is carbon, but what is the mass number of the carbon? So carbon can be carbon 12, carbon 11, okay, carbon 13, carbon 14, so on and so on. So what type of carbon Okay, then next step is you need to balance the mass number. The total number of nucleons on the left is the sum of atomic mass number. Okay. So nitrogen, the mass number is 1, and the single neutron is mass number is 1. Oh, I'm sorry. So the mass number of nitrogen is 14. Okay, and that for the neutron is 1. So in total, mass number from the left is 15, and therefore you should also have the mass number on the right equal to 15 as well. Okay, since one is contributed from the hydrogen. Okay, so leave us with 14. Okay, so it's at the end it's the carbon 14 is exactly what is the unknown nuclide. So this from the conservation of nucleon, this is how you can deduce what is the atom and then what is its mass number. So like I said at the beginning, we will look only into the conservation of nucleons and the conservation of energy in detail. Okay, but the rest too we will skip them. Okay, because the rest too does not do not because the other two conservations do not contribute to the calculation of energy. Okay, so because for the calculation of energy, okay, the Q value, you need to know what are involved before and what are involved after. Then you can calculate the Q value. Okay, so knowing what is involved before and what are involved after, you can calculate the Q value or the energy that you can get from the reactions. Okay, so which is the next example. The target nuclide is tritium. Okay, tritium is hydrogen. Tritium is hydrogen atom, but with two neutron. Okay, bombarded with deuteron. Okay, deuteron is hydrogen 2. So deuteron is hydrogen 2 nucleus. Okay, so you have one proton, one neutron. Okay, and deuterium, you is the hydrogen 2 atom. Okay, so the difference is this one is with electron. Okay, this one is without electron. So that's the difference. So meaning that deuterium is charged, okay, positively charged. So it is positively charged. Okay, so tritium is neutral. Okay, neutron 0. Yes. Similarly, deuterium is 0 in charge. So when you remove the charge, for deuteron, they have a specific name. For deuterium, they have specific name, which is deuteron. But for tritium, I'm not sure what is the name for the charge tritium. Okay, so which is why you have H3 and D. So D represent deuteron. Okay, so the tritium, okay, so the tritium is bombarded with deuteron, okay, deuteron P and A plus, positively charged. Okay, so you get the product are helium 4, okay, not alpha, helium, and a neutron. So what is the energy that you can get? Okay, so like in equation 5.5, so the mass uh, before the reaction, okay, the total mass after the reaction. Okay, so this is so tritium, the tritium before the reaction is around 2. Okay. Deuteron is around tritium around 3, tritium around 2, okay, and helium around 4, and neutron around 1. Okay, so if you only consider that, okay, you cannot get the answer correctly. So you have to consider this one up to 1, 2, 3, 4, 5, 6 decimal places. Okay, you have to go up to 6 decimal places so that you can calculate the difference correctly. Okay, so this is the mass before after the reaction, this is mass after the reaction, and multiply it with 91. Okay, it would be better if you use 91.494 instead of 91. Okay, so you get 17.579 mega electron volts. Okay, so I think that's for now. So that's for now. Okay, and therefore, what you seen at the beginning. Okay, so uh this is just the expression or the notation for a type of for any type of nuclear reaction. So in this given in this given example, so means that this is hydrogen 2 deuterium, okay, bombarded with neutron. You will get tritium and gamma ray, and this one deuterium bombarded with neutron. You will get tritium and a proton. Okay, if lithium bombarded with proton, you will get tritium and alpha particle. Okay, so so that's just so the title given here is just an example of nuclear reactions. Okay, according to the notation by the brackets. Okay, so that's only example. Okay, so that's all for now. Okay, see you again in the next video. Thank you.